of the semester, right?
No.
No, second. Second. I'm losing memory. Sorry.
Mid-September.
We're second seminar. We're happy to have Isaac from Fermilab, and he's going to tell us about BSM light meteor opportunities from ongoing thermal experiments.
Okay. Thank you, everyone. This is my first time to be here, so I'm very glad. I've seen many people that I have only heard about online. So, yeah. I'm a theorist. But I'm going to talk about something about experiments. But I'm a theorist. I'm so sorry if you asked me a lot of problems about hardwares and I couldn't answer. I apologize for that. So, this is a long-term story starting from when I was a very junior student. This is probably like my third paper or second paper from my whole career. And later on, there's some other works for that. And this is a long list of all collaborators that I've been working on. So all the way along these topics. So let's get started. We know that we have been working in the past decades, and we know we have a standard model of particle physics, and of course we also have standard cosmologies. We know we have quarks, we have leptons, we have gauge bosons, and we have the youngest particle in the final discovered particle, the Higgs. So we have a pretty beautiful and complicated, also standard model with a lot of particles. So we have still have some other questions remaining. We don't know what is dark matter. We don't even know whether that's really a traditional concept of particle. We don't know the original matter-antimatter symmetries. We don't know the source of additional masses or so it's a force, or just simple some kind of interactions of forces beyond standard models. And also we know there's some kind of more theory-oriented problems, like how to explain those unnatural parameters, and also know some more problems for astrophysical cosmology, like dark energy and Hubble tension, etc. Well, in all those kind of cases, we need some BSM theories. And one general way is to summarize things in simplified models. We call those mediators. And the mediators can mediate new interactions. That's why we call those mediators. But those are pretty general concepts, and those are some simplified models we build from, or by integrating out some other kind of heavy particles from EV theories. We finally can reach some kind of list of new interactions or new forces. This is kind of unexhaustive list. For example, I was pressing some more keys. For example, neutrinos can have some interactions among themselves, or some people have been talking about muonic forces, though I'm not sure how motivated they still think for this kind of models. We can gauge some kind of electron numbers. We can have some actual scalars in the scalar sector of standard models. So all these kind of new particles, they're aiming at creating some new forces. It can be Yukawa-like, it can be gauge interactions like, or any kind of general forms. Again, this is not an exhaustive list. So, well, different models have different kind of motivations. And all these kind of models that I listed before have come from various kind of big motivations from different pictures. But in general, we just call them mediators. So, for example, this is one example for the gauged lepton models. You will see this picture later for the specific motivation for that. But the point here I want to make is you can see people have been talking about the mediators for a really wide range of masses. They start from 10 MeV to a TeV scale. And similarly, you can talk about the scalar extensions for the standard model. You can introduce more scalar interactions between new particles, new scalars, and Higgs bosons. And also, scalar can possibly mix with Higgs so that they can also interact with the standard model particles and gauge fermions and gauge bosons. And this kind of scalar has also been strongly searched across a wide range of masses. They can be a MeV scale and they can be 100 GeV scale. And if I have space to show more of the plots and show more of the models, and you can also see this kind of scalar discussions for TeV scale or so. So those are a big range of the particles, and if you want to search for those.
So when you say mediator, so you mean just new particle, new bosonic particle, or is there some deeper?
Yeah, I just mean those. This is one specific example of one scalar. This is.
No, but just I'm trying to understand why you call it mediator as opposed to just new particle coupled to standard model.
Yes, but typically they mean gauge bosons or scalar bosons.
So-
we call mediators. We typically don't say don't include fermions.
So it's
Yeah.
mu boson coupled.
Yeah. That's actually not a really strictly defined terminology, but we
Just like that.
use it just kind of general terminology about how to mediate new forces and kind of
Wait,
mediate
sorry,
atoms.
dumb question. When you say new forces, are you talking like standard model forces, or are you talking about a new force, like is the mediator coupling the dark sector to the standard model?
I'm gonna write that.
Okay.
So far it's in the standard model, but I will go to generalize that.
Okay, sorry.
So, well, you can have different things. You can have TU scale things. We typically search for them in players. And typically, they allow to have pretty large couplings according to those current experimental bound. We can also have EV to MUV scale new particles. We can search for them in more various and beautiful ways in cosmology, in beam Thompson, and astrophysics. But because they're light, and typically we have large enough energy to create those, so they're typically constrained to have super weak couplings. So, well, for the heavy case, it's pretty interesting for sure, but it's also expensive to see those because they're heavy. We need more energies. These are cheaper to see. Well, they're constrained to be weakly coupled, but actually, coupling is weak doesn't mean they can have super small impact on the cosmos, on the universe that we have. But actually, those particles can do a lot. For example, let's focus on the standard model case for now, if the meteors only talk to standard model things. For example, neutrino self-interactions is a motivated model. Previously, people are motivating things or talking about that, okay, this can probably, arguably, solve the Hubble tension problem. This is one past examples, but now it's also under strong constraints. But you can also see this for some specific models that still works. And another example is if you have an axion-like particles talking with the Higgs sectors, you can, although the particles could be MeV scale and the mixing angle could be like 10 to the order -3 or even -4, you can still have a strong first order phase transition, modify the standard model, the electroweak phase transition somewhere is 3 in standard model. So people also have been thinking about the mediators could connect the standard model to the dark sectors. That's another way to define the mediators if you are interested in this kind of theories. Well, but this is historically, people have been talking about this kind of mediators parallelly in the topics that have been talked about before. And they have generally summarized the mediators to be this kind of forms. It can be a U1 gauge boson, and dark photon could be a specific example, but it also could be some other kind of Z prime. Dark Higgs is kind of a scalar that talks with a dark fermions in a similar way, similar to the standard model Higgs talk to standard model fermions, so which is the couplings is proportional to their masses. And in general, this kind of dark Higgs can talk to standard model sector via the mixing with the standard model Higgs. And you can have neutrino portals, axion-like particle portals, blah blah blah, all these kind of things. So this is quite a wide range of topics. And if you go back to talk about this kind of things, so this is one example of how dark photon, which is an example of those dark gauge bosons, they can talk to dark matters, and it can control the relative density of the dark matter. And this is the current status of these kind of things. And this is the mass of the dark matter. And this is a complicated defined quantities where cosmologists prefer to use this kind of quantities. So they include the mixing parameter of the between the standard model photon. They have the alpha coupling in the dark sectors, and a compare of the photon mass, dark photon mass, and the dark matter mass. So they can calculate, okay, along this curve, dark matter is correctly produced, but all the shaded regions are excluded, and the dashed lines are projected future sensitivity from experiments. And you can have different kinds of dark matter fermions. You can have pseudo-Dirac fermions, you can have asymmetric dark Dirac fermions, or you can even have scalar dark matters coupling to this kind of dark photons. So this is one example of how mediators control everything in the dark sectors. And another example is this plot you have seen before. You can gauge electron numbers, but you can also connect this kind of bosons to another dark sectors, and you can create a matter over antimatter asymmetry in the dark sector via a similar mechanism as electroweak baryogenesis. And the mediators can also transfer the charge particle asymmetry back to the standard model, and this could be a very excellent example of how mediators can transfer the particle asymmetry from between the dark sector and the standard model sector, and that could help us to solve the problem of the origin of matter over antimatter problem.
Sorry to ask a question about a sign, but L mu plus L tau is anomalous, right? It's like
Yeah.
L mu minus
I
L
think
tau.
they-
That's an anomalous.
I think they just got a typo.
Okay.
One of the early paper. So we have been talking about a lot of things about this different kind of mediator physics, Z primes, scalar mediators, all these kind of things, and they can have pretty rich physics, phenomena, and motivations behind those. So we're seeking for them from proposed BSM experiments, as we have been seeing a lot of shader regions that we have been working on during the past decades, 20 years, over 30 years. Of course, I say 30 years because I know for some kind of parameter space that I have showed before, the most up-to-date bound is still from the left, like 30 years, exactly 30 years ago. So, well, I still couldn't find any experiment that is sensitive to that. So, but okay. So the question is, have we really exhausted all the potentials that we have, especially except for those experiments that are specifically designed to search for those kind of particles? Are there any other possibilities that an experiment that was not originally designed to search for these particles, or even those experiments that were originally designed to completely motivated by standard model, not for beyond standard model physics? Is it possible to search for opportunities from this kind of experiments? So we have some beautiful ongoing new experiments motivated by standard model instead of beyond standard model things. For example, MUonE, I'm pretty surprised that this experiment is less known, but I'm going to give another advertise for that. It's an experiment that's motivated to measure surrounding alpha of QED, and finally extracting the hadronic contributions from this kind of couplings. They finished their test run in 2025. Well, the sad story is the original plan for this number is 2021. But because of the pandemic, they have delayed and postponed everything over and over and over and over until they told me just a few days ago that finally they finished the test run. Okay, good, very good. In HyperK, I'm going to talk about some more things about it. It's just the neutrino detector in Japan that's going to start taking data in 2027. They're aiming at measuring MeV scale astrophysical neutrinos. And we can have IceCube upgrade, we have Grand, those are aiming at high energy and ultra high energy neutrinos. They are both planning to start take data in the next few years. And also we have more. So, well, this kind of more things, I can't exhaust the list, but if some of the experts here know more about this kind of experiments, please tell me. I'll be very happy to talk about that. So, as examples, I will give two examples today. One is how to search for dark photons and dark matters at MUonE experiment, and the second one is how to search for neutrino self interactions at HyperK, Grand, and IceCube. So let's go to the first part first. Dark photon, as I showed before, is one beautiful model that you can't directly motivate it from standard model side, but because the dark photon is originally motivated from the dark side. But let's focus on the standard model couplings first. It's definitely a new coupling between standard model particles. So it, as original as all the kind of gauge bosons, they can have these kinetic terms, they can have the mass terms. In general, of course, to generate the mass terms, you have to have some new physics in the dark side here. Mixed with the electrons, the electric charge, so they can mix with the standard model gauge bosons and talk to all the charged particles in the standard model. And this is just the electromagnetic current in the standard model, right? So this is the mixing parameter epsilon that we're going to measure. The mass and the coupling strengths are not determined from first principle. If there's no experiment, then we can write any model to give the value to compute any point, but this is not determined from first principle. And then, because of the freedom of the choosing parameters, you don't know whether it's long-lived or not. It could be pretty wide. But from an experimental point of view, you can have a look at this kind of summarized plot. You can see the top part of this plot, which means the coupling is pretty large, is almost completely excluded for all the combination of all these kind of experiments. So this is the region where the decay is prompt. And lower down, this is the region where the dark photon could be long-lived if you create them from the experiment, relatively long-lived.
It's just as a curiosity. It looks a bit funny Why is LHCb this like tiny set of blobs in the middle? Like,
Okay,
why is their
good
sensitivity
question.
so specific?
I think for some reason they're specifically searching for the decay into muons. So they couldn't go to lower fast region because only heavier than 200 MeV allowed them to go there. And but for some hardware reason they couldn't go above.
Okay.
But they do have
And
a
then
further
there's like a
updated
gap.
projection for here. You'll see the projection.
Okay.
So this gap has been there for years, really long time. So this is in 2018, but if you have all the snow mass paper in 2022, you'll see the gap is still there, except for some dashed lines for future projections, but none of them has been true so far. I know there's a phaser. Phaser gives an official result in 2023, which is of course not including this paper because no one can move faster than the speed of light so that they can see the future and come back. So phaser is roughly start from here. Coupling goes to around 2.5, 10 to the minus 4. And then finally around here, which goes to 10.5. So it's basically from here to here. That is the phaser result.
Isaac, for LHCb, why is it just the little delta function blips?
Yeah,
Like, why is it so? But why is it so sharp? Why only at 0.2 and 0.4?
And there's like a gap in the
Yeah.
middle.
Yeah. I don't quite remember the reason, but I can check later. Yeah. I don't quite remember the details there.
It's producing too much muons at rest, almost, right?
Yeah.
At least one of these things.
Right. Yeah. There should have some reason there. I can go to see for that. So another thing that we can talk about on dark photon is we can talk about dark matters. So except for those very simple Dirac fermion dark matter, I'm going to talk about another next to minimal case, which is the inelastic dark matter. I'm not going to talk about a simple case of dark matter because that's almost excluded in the parameter space that we're interested in. So an inelastic dark matter means dark matter has two almost degenerate mass eigenstate, chi1 and chi2. Almost degenerate, their mass is pretty close, but chi2 is slightly heavier. And the interactions is off diagonal with the dark photon. So the annihilation channel for the dark matter, if they want to annihilate to a standard model of sectors, is via tree-level interactions like this. So this is a beautiful model mentioned like almost 25 years ago by David Smith and Neil Weiner. So other than dark photon parameters, now we have two parameters. It's the mass of these two particles. But typically we parameterize in a way of one of the mass and then the splitting, because splitting is typically small. And it makes more sense for us to just compare the splitting relative to the mass scale. And usually in experiments, we search for this kind of inelastic dark matter in the following way. If dark matter is created, this is one example in the muon beams, but it could be similar to some other kind of beam accelerators. By some kind of interactions, dark photon is produced, and dark photon immediately decays back to dark matters, a pair of dark matters. Chi1 is dark matter, it just becomes missing energy. Chi2 is heavier particles that will further decay semi-leptonically. This is dark matter, and this is a lepton pair. And this could be displaced in the primer space that we'll be interested in. And this is another Chi1 that is another mixing parameters. And typically the decay length is of centimeter scale for this kind of benchmark parameter choice, which is the dark matter mass, dark photon mass for 100 MeV, mass splitting like this, and for this. I'm going to show you the parameter plot for that. But let's emphasize again, so you can see the primary particles, primary beam particles from the scatterings, and also displayed vertices, or MET. And so if you search for tracks, you will see 3 tracks, and the leptons are from displaced vertex. If you search for MET, then it's just a missing energy.
Sorry, it's a little bit faster for me. What motivates this type of model other than the mass splitting gives interesting phenomenology?
What motivates this inelastic dark matter, right?
Yeah.
So historically, that is given by this paper. There's an anomaly called Dama anomaly. It's
Okay.
basically some experiment observes dark matter, observes something, but the other experiment doesn't. So they're trying to explain why.
Okay.
But this kind of splitting also plays a role of this is the traditional trick to in model building to avoid direct detection and also indirect detection.
But this Dharma deeper anomaly, that's
Yeah.
been somewhat resolved, right?
Yeah.
I
No,
thought that-
is it?
Well, some people did an analogous experiment. I thought
Oh
it was
yeah.
the exact
But that was
same.
but
But the experiment itself, yes, was never
Yeah.
explained.
That's 20 years ago, but really recently, the motivation, I think from my point of view, I think the motivation quite shifts. This becomes a trick to avoid a lot of experiments, and that's pretty straightforward. The source of this kind of inelastic dark matter could be straightforward because you can simply have a dark matter couplings, just a regular couplings, this kind of couplings. But you can also have some kind of MUonE mass terms like this. Well, this kind of terms can be easily generated if you have some loop from, for example, some kind of higher operators, or from some quantum diagrams, or for example, in Higgs naturally comes with this kind of mass weighting. And if you calculate mass eigenstate, this is the direct mass term, this is the MUonE mass term, and that naturally leads to this kind of inelastic dark matter. That is notoriously difficult to detect because direct detection doesn't work. You have to upscatter from the lighter state to the heavier state. And if the mass splitting is large enough, you don't have enough kinetic energy to do the upscattering. So direct detection won't work. And indirect detection also won't work because in the current universe, only Taiwan exists. And they have no annihilation partner, so that indirect detection also fails. So that's kind of the trick from model building point of view. If you have these kind of things, then you have kind of space to survive. So, for example, this is the current status. You will see a similar signature compared to dark photons. Like the top is completely covered, and this bottom is almost covered, but there's a gap here. And the question again is, how do you want to probe this gap? So, you'll see there must be some common signatures between this plot and the dark photon plot, because they have a similar shape, and they all fail in a certain region. And that is actually because if you estimate the decay length of those particles falls into that gap, inelastic dark matter have a 10 centimeters decay length. Dark photon, okay, this is also a few centimeters decay length, depending on these kind of parameters. But all these parameters are chosen to fall into those gaps. So the question is simply, what are the experiments that happens to have the geometry that can search for displaced vertex with this kind of distance? So that is the problem, why we still haven't seen those. We simply don't have an experiment that lives in that region, in that geometry. So let me remind everyone about how do we search for this kind of displaced vertex. We basically have an interaction vertex that creates some particles, and the particles move away and decay somewhere else. And you have to have some detectors here to reconstruct the trajectories so that you find, oh, these two trajectories are from a common vertices that is displaced away from the original interaction points. So from the geometry point of view, you should design a decay volume. That is mostly because of where is your detector from the interaction points. And this is the decay length. For a certain decay length for a given parameter, this is the probability that it could decay within this kind of volume. And of course, the expected decay length is the boosted lifetime. So let's have a look at the main role of our today's story is the MUonE experiment. Let's see how that can work. So this is an experiment originally proposed in 2016. That I remember that is the first paper where they first came out. They want to use the SAR M2 beam. This is 160 GeV, not 150 GeV. But they never updated the plot in their white paper. So this is the geometry of the whole experiment. So they have 40 identical stations. I'm going to tell you what exactly is the station. So after the 40 identical stations, they have an etal, they have a muon filter, so that they can exactly know which one is electron, which one is muon, which one is some other kind of particles that is giving you a charge to track, but it's not electron or not muon. For example, charge pion. If you have charge pion ionized here, they can tell you, oh, this is not electron, not muon. They're aiming at measuring this kind of process, very simple QE process. They want to measure this so that they can extract the hadronic contribution for only electron. Well, muon J-2 is partially gone, but they already have the money, so they're going to run it. so for their original purpose, if you want to measure a 2D process, a 2D process will have pretty strict phase space, and you have only two variables. You have two angles, and these two angles are related to each other and have a strict one-on-one correspondence. Otherwise, that's not a 2D2 process. So a strict elastic scattering of a 2D2 process should fall on this curve, right? So this is the outgoing muon, and this is the outgoing electrons. They have different angles that we will measure it. So in their original proposal, to extract the elastic scattering cross sections, the only thing they need to do is to identify whether this event is elastic or not. And to identify it, they can simply measure the angle of the outgoing muon and the outgoing electrons. If they fall onto this curve, then yes. If they deviate from the curve, then no. So for this purpose, they have to design, or they want to design, a system with a pretty high angular resolution measurement. So if you go back to have a look at this structures, well, this is the structure for them to have a look at all this kind of design. Muon energy modules, well, they have super high muon energy beams, so they don't need to worry about the scattering angles are too large. This is pretty forward moving, and scattered electron is also pretty forward moving, so that they can arrange everything on line, everything on straight line. They have 40 modules, and they have integrated luminosity of this, and they expect to have these 2 years of data taken.
Sorry, dumb question. These issues with like muon cooling, that's not an issue here?
Sorry?
Like the issue with like muon cooling and everything, does that pose any problems here, or is that not an issue?
I don't think that's kind of an issue. Like if that's a muon cooling, I think that's a different kinematics. If you want decay somewhere in the region, or.
So muon cooling is like, can you get a collimated muon beam, right? It's why the issue with like the muon collider.
I understand the question. I do have a conversation with some other muon collider guy. I think I talked with Carrie before, and I asked her why that's an issue for muon collider, but not for this kind of muon beam experiments. And the answer is simply because the issue is not the same seriousness at different energies. It's simply for this kind of energies, it's much less of an issue. But I don't know exactly the technical reason, but that's
Maybe you don't need the phase space to reduce.
Yeah, the experiment seems to be pretty confident on this muon beams for this kind of energies.
They haven't taken data yet, but they will.
Yeah, they will, because they already finished the test run. And they plan to spend another year for data analysis. They told me that's going to be a whole year, start from now and until the end of 2020, 2026.
And the test run had the 150 GeV MUonE beam?
Yes, yes, but less stations. They probably only have 5 stations in the test run or so.
Where did they get their beam from?
Hmm?
Wait, how did they generate the beam?
Generate the beam?
Yeah.
There's some source from CERN, I forgot what is that. For CERN M2 beam is just a pretty standard beam that a lot of things can use. NA64 is also using this beam, right? I remember. Yeah. Okay. This is the structure of a target. You have a target here. So this is a beryllium target. There was some discussion of whether we should replace beryllium with some kind of other kind of things, but they finally made a decision for that. They have a thickness 1.5 centimeters, and they have 3 excellent tracking stations. And the distance between one module and the second module is exactly 1 meter. And the distance between the first tracking station to the target is 15 centimeters. So if the displaced vertex happens here, they can penetrate 3 tracking stations, ensures a pretty high angular resolutions, pretty high resolutions to reconstruct trajectories, and you'll be able to seek for this kind of displaced vertex. So, if you really want to perform long-lived particle searches, you can have you can have pretty good geometry just happens there. Well, this experiment just happens to be good there because they have pretty good angular resolution, so that this happens to be good for displaced vertex constructions. And the geometry just happens to be good because, as we said, this is 15 centimeters, and that exactly falls to the gap that we want to fill. And they have a particle ID system, and also those kind of trackers has pretty high sensitivities. So if you have some background events, that happens to hit the trackers, they can tell you. So that's also pretty good for background rejections. So all these kind of things make it happens to be a very good candidate for a long-lived particle search, other than these original motivations. So if you want to search for dark photons, you could just consider this kind of scattering process. MUE, you can radiate out in A prime at any stage during these scatterings. So you can just have this kind of 3-3 process. And A prime just decay back to E plus E minus. Unless you can go to as high as 200 MeV, they can probably decay to muons, but that's not the case. You just don't have that kind of large center of mass energies. So they're not going to decay to muons, just electrons. And they would have a long-lived lifetime and has a few centimeters away from the target, which happens to be detected on experiment. So the topology will look like this. Muon, which is scatters coming out, electron scatter coming out, and you have dark photons decayed a few centimeters away from the target. And the 3 black things are the tracking stations. You can have hit, connect these 3 hits together. Okay, this is one trajectory. I reconstruct that. Hit, you reconstruct this kind of trajectories. You can find the trajectory here, and then you can find the displaced vertex here. So finally, you can require them to enter the cal or muon as an selection event if you want to reject the background, but that depends on how the background looks like, and depend on simulation that I will be talking about later. If you want to search for inelastic dark matter, so that's because of timing reason. Initially, we don't know we can just consider mu to n elastic scattering. We suspect that we need to scatter with the original electrons, and we want to see the original electrons at another charged track to help us to reject the backgrounds. But after a lot of work, we just found it's probably not needed. So in the next paper, we didn't consider scattering with electrons. We scatter on the nucleon, and which provides a much higher center of mass energy, and you can go to a much better region. So in this case, mu scatter with the nucleon won't move, of course, and dark photon comes out, and dark photon goes to the dark matters, Chi1, Chi2, and Chi2 decays back to electrons, and this is the displaced process. And you can search for this kind of a final state electrons, which is displaced, and also for this primary muon, so that's a 3-track search with displaced decay. So if you have a quick close look for the decay volume, it's just like this. This is 15 centimeters. And we require a delta Z tail from here, from the detector, from the tracker, and also from the target, so that we can avoid misreconstruction for a prompt vertex as displaced vertex. And after thinking about that, we are ready to go to see the models. And the last thing that I want to mention before that is the PID system. The PID system is at the very end of the whole system, which is 40 meters away from the first target. So if you want to search for the original standard model process, that's okay, because the muon electron scattering is like, muon is really energetic, and electron is really light. A muon has a pretty high energy that can ensure it to make through everything and make it all the way to the end, enter the ecal and the muon system, and we can identify that. But if you want to search for some BSM process, and the BSM particles are taking away some energies, the charge tracks, the displaced vertex of the charge tracks, and also the primary muon may not have large enough energy to penetrate all the faulty modules. And after some back and forth discussions with the experimentalists who make the original design of this experiment, we just finally decided to use only the closest 5 modules, so that we can avoid losing too many energy during the way penetrating everything, so that which will lead to a misidentification from the PID system. Okay, so the backgrounds, 2 types. One is we misreconstruct some kind of prompt vertex as displaced vertex, but as long as we require an decay volume that is pretty far away from the target, it should be safe. So another way is really physical. It's like a standard model indeed can have some this kind of displaced vertex, but these are not electrons. This can be pions. K goes to pi, lambda goes to p pi, these kind of things. You can have charge. You can still have some charged tracks, and the only way you distinguish this background from our signal process is by the PID system. You can see this is a pion, this is not an electron. So that's the only way you want to do. So after doing some simulations, we know that is okay. The number of those kind of backgrounds that satisfy this topology is under control, and PID has a pretty reasonable efficiency will be enough to reject these kind of backgrounds. For time reason, I won't reach that detailed number for now, but you can ask me afterwards. So after rejecting these backgrounds, we can see the reach. This is the dark photon. Again, we're considering MUonE to L transparent. So this is almost arriving at around 70 MeV. And for dark photon, we are filling this gap. We're currently having an ongoing work, which is pretty trivial after we have all this kind of technology equipped, which is simply if you consider the MUonE scatter on the nucleons. And preliminary result can tell you we can go to like around 250 MeV.
And just to be clear, this is the dark photon only model.
Yep. Yeah.
What's the NA64 10 to the 13?
10 to the 13 is that's the future projection for the NA64 mu. You have that's exactly the same MUonE beam. And NA64 has another different kind of design, different geometries. And if they plan to have different number of muons on targets in different years, and this is one projection for the total muon on targets 10 to the order of 13.
Say that again. What is 10 to the 13?
Muon, total number of muons on target.
Total.
And you can also see some other projections. LHCb run 3. Well, they have talking about this for years. Yeah, we can wait to see that. And that's part of the LHCb project. And HPS is heavy photon search experiment. So they also have some other different groups there. I don't know why they designed it that way, but this is the projections.
So HPS is going to be at SWAC or something?
It's heavy photon search experiment.
Yeah, where is it?
I think it's in SWAC, but I don't remember exactly. Check that.
What's its status? Is it going to happen?
I remember I have one slide. I have one backup slide summarizing that. Let me search for that first.
It's okay. You don't do
Oh, that's what it is. Should be somewhere. Yeah. Yeah. So they're going to start in next year and beyond in the next 3 years or so. I remember it's 3 years. So they're going to reach their full luminosity there. Yeah. NA64 this around. But that is beyond the long shutdown 3. And they also plan to do a 10 to the order 14, but that's even longer. So no one knows what's the exact schedule there. It depends on which things changes and how things goes. Okay, this is the result for the inelastic dark matter. We can exactly cover this thermorelic, and other bounds are existing bounds here. You can have some other kind of projections from future experiments, LDMX, BDX, and MUonE and things like that. And also a project for Belly 2, whose analysis hasn't been found yet. And this is our projections. I also have to explain this. This is a trick from theorists, so some experiments may be angry for that. That is because I have mentioned the energy loss when the particle penetrating all the modules before they enter the ECAL at the end. So if you want to make a careful analysis for that, you may need to simulate how energy loss is during passing through those materials. But you can also mimic the behavior. You can just use a brute force to add a cut there. Like, say, energies below this threshold cannot be identified, and we're going to discard this event. So that's kind of a trick from theorists. So, yeah. So this is kind of a mimic of that kind of energy loss behavior. But the result is not that sensitive to that, and actually, E around 1 GeV seems to be the most reasonable cut, and this seems to be too aggressive. This is a little bit. This is not so aggressive, but this is too conservative. But this should be reasonable according to what we have been talking about back and forth with experiment was. So let's go to the second part. Let's talk about neutrinos. So neutrinos are a different story. And we're not going to create any experiments, but we're going to talk about some other observations. So neutrinos is a kind of a beautiful particle, or also a mysterious particle. It doesn't even seem to be below the standard model. I know some people who just who blatantly say that neutrino is just from another sector, is not standard model. It looks pretty weird because neutrino we know in standard model is strictly massless, but we know it's massive from the neutrino oscillation experiment. So this is the oscillation behavior of the neutrinos. You see, you need for sure needs a non-zero mass splitting between the mass eigenstates so that they can oscillate. Or theoretically, that's pretty straightforward. If you don't have mass, then you can talk about different eigenbase between mass eigenbase and gauge eigenbase. So there's no oscillations. But you, in any case, you want some BSM theories to create an neutrino mass in a model building point of view. For direct mass term, you need a right-hand neutrino. For minor mass term, you for sure need, at least you have to write this kind of high-dimension operator. But high-dimension operator also means you have some UV theories before. So it's almost guaranteed that if there's new physics here, talking with neutrinos to generate non-neutrino masses. But similar to the standard model, like standard model Higgs is responsible for all the particle mass in standard model, and of course, aside for the web of the Higgs, you have the dynamical Higgs field, which is interacting with everything. If you have a mass from somewhere else, it also kind of implied, I'm going to say implied, I don't want to say too aggressively like this for sure gives you in kind of BSM interactions, but it's kind of implies that it could be some kind of BSM self-interactions between neutrinos in this way. So the question is, can we really search for that kind of self-interactions? And well, before we talk about anything, so I just want to say that let's just define the simplified model this way. For sure, you can think about, we can couple this kind of thing, like we make the coupling to be a 3x3 matrix and talk about different combinations. For sure, that is good. And I know a lot of neutrino self-interaction papers are talking about those kind of cases. Yeah, but this is a talk. This is not a strict paper, so I'm just giving you this kind of simple things. Yeah, for simplicity, you just assume this kind of universal couplings. You can also think about G tau tau or something. And I know there are works in that, and you will see that class later. Yeah, so also there are some kind of bounds. For example, at MeV scale, for a universal coupling, you have lab constraint. Those are mainly for rare meson decays. You have BBM because you don't want to thermalize that kind of particle so early and to contribute the ineffective to the cosmology and to destroy the BBN. Like that. But for EV scale, the ineffective constraint, this is from CMP because the temperature and mass scale goes lower. The bound for ineffective gradually goes up. And there's also bound for neutrinoless double beta decay. And you also have supernova bound. But there's a plan of space after that. And that's the current status of the neutrino self-interaction mediator.
Sure, why does the CMB bound increase with increasing in phi?
Why increase?
Yeah.
Okay, so the reason is this. The problem is how do you want to thermalize the particle phi? So you basically have these two processes. Fermilab. So this is one process. And you can also have this. Right? So when the temperature goes lower and the mass goes lower, well, this is suppressed by G squared, right? The amplitude, I'm talking about amplitude. And this is only G. So in principle, this is larger. But when the temperature gradually goes smaller, there's less and less particles that could give exactly the good center mass energy to this. For example, it's kinematically forbidden for, let's take a massless limit. If this is massless, this process is forbidden, right? It's like 2 electrons can never go to 1/3. It's kinematically forbidden. So when this is heavier, this is not that kinematically suppressed, but if this is lower, you can just do the calculation, take the summary average for the initial state. You'll see that this is suppressed by the small mass of this process. So because the G suppression is small, so this is dominating for the high mass region, but when the mass goes lower, the main contribution of the thermalized process is kinematically suppressed, and this diagram gradually goes away. So you only have this, and this is G squared. So the bound is going. If you see a lot of papers talking about models, Gordon also have papers talking about this kind of light Z primes, you also have the behavior pattern for this kind of thing for the same reason. Inverse decay is dominating for the heavier region, and this kind of secluded annihilation is dominating in the lower region. So they have behaved pretty differently.
Sorry, F is.
Inertial state fermions that the phi couples to that thermalize
Like
phi in
electron or
plasma. In
neutrino?
this case, it's neutrino.
Oh, okay.
In this case, it's neutrino. But this is a general behavior for any kind of mediators. So I just write F. I just write neutrino.
But for an electron, I could have E plus E minus to phi gamma.
E plus minus to phi.
But anyway, sorry.
Yes.
Neutrino, I understand. Okay.
Yes. For electron, yes. You can have that kind of things. So that's a different story. But you will finally still see this pattern. For example, you can have a look at one of the results for, like, gauge L mu minus L tau Z prime. You also see this behavior because you also have, well, you include the third process, you will also see some kind of kinematic suppression for some of the process there. And this still, you after all, applies out a lot of diagrams there. So you should expect some kind of weaker down. Just not this, maybe the shift is not that strong. The shape is similar. Okay, so, well, all these kind of things, we know there's some early cosmology things, the BBM and CMB, and neutrino double beta decay and reminiscent decay are some experimental source that we can create in the lab. But we can also consider some kind of astrophysical source for that. Like, if we really have that, I'm going to talk about where are the neutrinos that we still have in the current universe. One example is the cosmic neutrino background, which is notoriously difficult to detect, because we know that neutrino itself is hard to detect. It almost doesn't interact with anything. Similar to the CMB, we should have a cosmic neutrino background, which also just gives by neutrino freeze out. CMB temperature is given by this familiar formula. It should be given by this energy, which means, okay, neutrinos are almost highly non-relativistic, have pretty low energy, and it's neutral, so we have almost no way to detect that. But we also have some astrophysical neutrinos. Astrophysical neutrinos can come to the Earth. They are pretty high energetic. And we have various ways to detect those kind of astrophysical neutrinos. And different experiments are aiming at detecting different neutrinos from different energy windows. But we have the background surrounding our Earth, surrounding and penetrating all the whole universe. So when the astrophysical neutrino coming to the Earth, along the way they are penetrating the CNB path. So if the self-interactions happens, astrophysical neutrinos and the CNB neutrinos may interact. And they can create some kind of scattering too, just kind of elastic scattering goes to other two neutrinos, or create some of this kind of mediators. So anyway. Well, for example, this is an example of high energy neutrinos. High energy neutrinos defined as neutrinos with energy in this range. I'm going to talk about more details about the source later. But the free propagation of astrophysical of this high energy neutrinos is this black line. This is energy and this is the flux. So the flux basically follows a power law. This is a log scale, remember, so the straight line means a power law. But with neutrino self-interactions, they could be distorted. And you can have three resonance peaks. These two peaks are pretty close to each other, so you won't distinguish that. But there are three resonance peaks. And this will lead to some kind of exclusion for some kind of couplings. This is in pioneer work by John Beacom and his postdoc and students and collaborators in 2021. And this is given by the IceCube Gen 2, which is even longer time period experiment.
And those resonances depend on the details of the self-interaction.
Also depends on what kind of neutrino mass you have. Yeah. So still just given by incoming energy, right? Yeah. Incoming energy, CMB energy, and how whether the relay has a neutrino mass, or the mediator has, right? And that also depends on neutrino mass. Because if you assume CMB is neutrino background heavy, non-relativistic, so the energy is just given by its mass. So there are many different sources. I'm going to talk about three examples today. One is DSMB, it's diffuse supernova neutrino background, which is MeV scale, and this is the flux. One is called high energy neutrino. Ranges from 10 to the 3 GeV to 10 to the 8 GeV. This is detected by IceCube. And the other one is called ultra high energy neutrino. It's going to be expected to be detected by Grant or IceCube Gen 2. This is defined as energy larger than 10 to the 8 GeV. And they have, all these kind of things has different behavior. So the first one, which is the one that we have the best understanding from the theory point of view, is called DSMB. It's called diffuse supernova neutrino background. So we have mentioned supernova source of particles on this journal called just a few hours ago. So we mentioned that if a supernova is pretty close, you can, or maybe you're more likely to see some particles from that. But if they're far away, you're less likely to see the particles from that. But Earth is nothing special in the universe. We have tons of supernovas in the whole universe. So if you focus on one supernova, then at the center of supernova, place the center of radiation in a supernova, and you have a big circle surrounding supernova, and Earth is only one point on the surface of the supernova, and it only receives one small portion of the emitted particles suppressed by 1 over the distance square, right?
So this rate is
Yeah,
for the whole Earth.
Yeah, definitely. But if you integrate over the whole universe over the causality reach, and you will see integrate over the whole range of all the supernovas that you are possibly going to see, and that integration range will compensate the suppression of the distance square. So, because that's an integration of all the possibility distribution of the supernova, that's called the diffuse supernova. And that's the source of the initial background. That is the concept given by John Beacom many years ago. So supernova is basically has the particle energy distribution following the Fermi-Dirac. So after the cosmic evolution, what you can see is in just a redshift distribution of the Fermi-Dirac distribution. But of course, the distribution depends on the temperature, which is currently an unknown parameter, right? The supernova neutrino. We don't know the temperature, but we just roughly know that they should be around this range. And so diffuse supernova neutrino background is almost a guaranteed source, and so that we have experiment that aiming at detecting that. So one of the experiments that I'm going to talk about today is the hyper-MUonE. That is an experiment that is going to start on 2027. Expect 50 events per year, and that will take many times. We're not sure, so I just write future here. The name is pretty interesting. It's actually Kamioka, in Japanese name, NDE, Neutrino Detection Experiment. So people who don't know Japanese will just pronounce it MUonE. I hope Japanese people won't be angry about that. So that's a big, huge water tank to build a water Cherenkov detector. And the detection process, they want to detect the electron antineutrino. And they want to detect this, the scattered positrons by Cherenkov radiation detectors. So that's the dissonance of K and super K. This is fully funded. These two both have Nobel Prize. So of course their grandson has almost every fund that they want. So it's already fully funded. It's finished the construction. They're going to take data. So that's a signal. That's not a background. That's a signal from the from the supernova. Okay, the second thing is the high energy neutrinos. High energy neutrinos is kind of different thing. It's almost opposite to DSMB. DSMB, we know a lot of things on theories, but we didn't see that so far. But high energy neutrino is the opposite. We have seen many events in IceCube, and these are the event bars, the flux. And that could be numerical fit to be a power law by IceCube collaborations. So this follows the power law. But we don't know what is the source. Really don't know. The only thing I know is that we see that it's a power law. But no one knows why do we see that? No one knows what is that. And the energy range is like that. Ultra high energy neutrino is another different story. We haven't seen anything about it, but we know that there are some ultra high energy cosmic rays, like the protons. That's for sure that we already have a lot of studies on that. And we know that protons scattered with gamma can create some other kind of hadrons, and this can decay, and that leads to some neutrinos. So there are some understood source about the source of the ultra-high energy neutrinos, but we don't know whether there are some other sources of this ultra-high energy neutrinos. There are some guaranteed, already known sources, which is the thing that I just mentioned. We just don't know else. We see one event in KM3 event net, 200 PE. Might be here. We don't know. Might be here. So we are aiming at seeking for this kind of things. The cosmic P follows a power law for sure. So maybe there are some similar sources for high energy neutrinos, but we don't know. But because P follows a power law, the scattering of the scattering result, and which finally produces a neutrino flux for the ultra high energy neutrinos, should also follow the power law, but you'll see this. This is because they have some other kind of, because the cross section depends on the energy. So that breaks the power law. So this is not a power law, but the source is a power law. And we expect Grand and IceCube G2 can see this kind of source. Grand is kind of antenna that has a worldwide big project, and that spread over many countries in China, in Europe, in Mongolia, and many other different countries. They are sensitive to top neutrinos, and they stopped construction in 2025 and plan to start taking data in 2030. Let's hope they finish their construction on time. IceCube is another detector based on the ice region, which is the South Pole. They're going to take data in a few years for the IceCube upgrade. The current IceCube has already seen high energy neutrinos. And IceCube upgrade will see more things from high energy neutrinos. If you have IceCube Gen 2, that could be sensitive to ultra high energy neutrinos. Mm-hmm.
This is a super naive question, but how does a radio array see neutrinos at all? Like, how does that work?
I don't know.
Previous one?
I don't know either. I'm also trying to talk to them to see what happens there. Yeah. IceCube is supposed to be sensitive to all neutrino flavors, so that's a pretty good news for us. Okay, let's go back to our topic. We're going to use that kind of things to detect neutrino scatterings, and so whether you can hit on the resonance is the biggest problem. If you hit on the resonance, you see a lot of things. If you don't, you see pretty small scatterings. But that depends on whether neutrino is relativistic. If a neutrino is not relativistic in the cosmic neutrino background, then what it contributes to the center mass energy is just the mass. And the other part just depends on the incoming energy of the neutrino. But if neutrino is still relativistic currently in the cosmic neutrino background, then the energy it contributes depends on the temperature of this cosmic neutrino background, right? That's the temperature, the kinetic energy. And the other part is still the incoming energy. And you will see that this sharply gives a pretty different behavior. Like for the same incoming energy of the neutrinos, relativistic and non-relativistic gives completely different result. Non-relativistic can probe the M5 and 1.5 keV, but this gives 80 eV. So that's really different behavior. Then you will ask whether it is relativistic or not. Let's have a look at this mass splitting. So even if the lightest neutrino has zero mass, you just add the mass differences up and up. You will see the mass 2 and the mass agency 2 and 3 are much heavier than the current C cosmic neutrino background temperature. So at least these two flavors are really non-relativistic. But the third one we really don't know. Some people, we know there's a DESI data giving an upper limit on the total neutrino masses and even favors negative mass. That's not physical at all, but that's just pure mathematics. They favor that, but I know some people don't believe that. But that could be a hint that we really have this kind of, what could be the lattice favor is still relativistic or even massless. We don't know.
So Isaac, you're at the hour now?
Almost. Yeah, I'm almost there.
Okay.
Almost there. Okay, good. So, non-relativistic case, you have this kind of power spectrum annihilation if you assume this kind of total neutrino mass. Right. And if you have an ultra-relativistic case, you will see the resonance is widened because that's a smooth distribution following the temperature. So that could be a widened dip instead of the sharp dip. So we can then just combine different possibilities. And work has been done as high energy neutrinos with a non-relativistic. This is this plot. The mass of the mediator is at MeV scale, and coupling is equal to 10⁻⁻2 to 10⁻⁻3. And if you go to DSMB plus relativistic CNUB, you can go to EV scale, can probe a huge range for the result, 2 to 3 orders of magnitude stronger than the current bound. If you go to ultra high neutrino plus non-relativistic, this is a really recent work, and you can probe these different results depending on what kind of detector you're assuming, but this is MeV scale things, right? This is 10 to the order 6 EV, so this is MeV scale things. And the coupling again becomes like this. And we have a preliminary result for the ultra high energy neutrino plus relativistic. This is a preliminary result. The estimation is simply based on the mean free path argument. You just require the mean free path is smaller than the current universe. For consider different incoming neutrino energies, you can have different curves. And the final curve should be just a connection between these curves. So in this work, we use the mean free path estimation, and the final result after solving the Boltzmann equation and calculating the detector response is almost exactly the same as the estimated result. So we expect maybe the final result should be just around here, a smooth connection between that. Of course, that up to some uncertainties in detector responses from chi-square analysis or so. Okay, it's a long talk, long journey, but yeah, I hope this talk can motivate people to think more about the possibilities from various experiments that all that has been designed to some purpose that seems to be irrelevant to what you're thinking about. So all these experiments that I have been talking about is for standard model-based motivations, but they can be sensitive to many BSM scenarios, and none of these proposals require extra hardware improvement or extra setups. If you want to add something, if you add or if you want to improve the sensitivities, no. There's zero money cost. You only need to do more analysis. So that could be I personally think that could be one of the most interesting scenarios in the next 5 to 10 years. So that could help us to build more models or motivate more models without cost of extra fundings or extra monies, but we can just take all the use over all the current thing that we have. So I'm happy to answer any questions and of course further discussions. Thank you.
So in those last plots you were showing with the different, the ultra high energy or the very high energy, the different energy regimes, and whether it's the relativistic, non-relativistic. Sorry, are you using IceCube, HyperK? What experiments are you using for this balance?
For this one? This one is grand.
Okay, but each of the different plots you were showing was using a different detector?
Yeah, there are some different detectors. You have to choose the detector that is aiming at detecting the corresponding source. For example, if you consider ultra high energy neutrinos, then you have to consider Grand and IceCube Gen 2 because only they are sensitive to the corresponding energy range.
Then where is Grand?
Grand is many different antennas across the whole world. Many countries have that. It's a big project, cross-country project. Some of them in Europe, some in China, some in Mongolia. Yeah.
And these are Cherenkov telescopes?
No, that's it's like this. Animus. I don't know how it works.
Yeah, so maybe this goes back to Maurice's question. So wait, how is that?
I don't know how. I don't know how.
So when neutrino is like
Yeah, maybe
interacting
Anna has a
in
better
the
result.
atmosphere, it's gonna produce air shower, then gonna
Yeah.
produce
Radio waves.
signal.
Okay,
and you
so
can
it's from the
detect that.
showers.
But wait, so they cascade, but then where do the radio waves come from exactly?
From the shower that was produced by the interaction of neutrino. From for example, tau neutrino will create a tau, and the tau has short lifetime. It will decay to a bunch of particles which
Right.
emit radio.
Um,
So I think they look for stuff where there are valleys, and they kind of try to see some particular geometry to detect the tau neutrinos like that. So in a way, in some cases, you could know that if something is coming from the air, it can be only, for example, neutrino, and that if it crosses particular length of the material for particular energy, then you kind of can imply that was tau neutrino.
is there a spectra of photon energies from this?
I think so. I'm assuming they model that. I don't know. But if you want, the radio emission is from the shower. It's not from like neutrino itself.
They reconstruct. Yeah.
And sorry, this radio emission is in frequencies that are not polluted by other sources? Or?
I'm not 100% sure, but they try to do distant things, so they might be. I don't know about that, sorry.
Judging by the size, you might get the size of the array. It's a
Yeah.
little hard to tell from here. That would give you a sense
Really?
of the wavelength they're trying to detect.
No reference point.
Oh. This from the website.
Any other questions?
Very quick dumb one, sorry. Just wondering about these displaced vertex searches that you were looking at. I was just wondering, like, do you have to trigger on something? Like, do you have to do any specific trigger settings in order to do the search for dark photons compared to other displaced vertex searches, or is that something that you could play around with to kind of maximize your signal?
Okay, good. So you're asking for what's the specific trigger to, do you want to distinguish that is a dark photon or some other?
Yeah,
image?
yeah.
I don't think you are able to distinguish that. It's
But I
like
mean,
if
are
you
you
don't see a
doing-
displaced vertex, you can for sure do theory interpretation.
So any
use
displaced
the-
vertex search
Yes.
you could use, there's nothing you couldn't do it,
Yeah.
add anything?
Yeah, it's kind of like if you didn't see it, if you see some displaced vertex, then probably you really see some BSM things, then I think the experiment will do that. But if you didn't see any beyond standard model displaced vertex, then the next step would be how many BSM models will predict this kind of displaced vertex and how they can be excluded. Then that's just the next job to consider.
Thanks.
So let's thank guys if you